CMC Microsystems, and we're presenting an update to a project that's been running over the past year or so to develop a PDK design environment for a heterogeneous multi-technology interposer platform for 2.5D integration. I'll give a brief introduction to CMC Microsystems as well as the objectives of the Interposer platform. And then Innotime will provide an update to the Interposer platform technology, including results to date. Then I'll talk about the products and services roadmap, and then we'll have Q&A at the end of the conference call. CMC Microsystems is a not-for-profit corporation that was incorporated in 1984. We're the creator and manager of Canada's National Design Network, and our mission is to deliver core micro-nano innovation capability across Canada. Canada's National Design Network is a collaboration between 62 colleges and universities across Canada, 850 or so companies with whom they are collaborating in the design, manufacturing, and test of microsystems prototypes. Annually, we connect with over 1,100 faculty and 4,000 graduate students and members of the research teams of those faculty. We measure our success through the publication of papers, awards, patents, industrial projects, startups created, and development of HQP moving to industry in Canada in the sort of microsystems industry. CMC provides 5 key services. We provide microsystem design tools and methodologies for university and college participants, fabrication services so that they can transform their designs to working prototypes, equipment and services for product testing and validation, training and support services, and network management, including connecting faculty and industry and CMC for collaborative projects. In terms of what we provide CAD tools for design and simulation of microsystems devices, manufacturing and fabrication services, test and verification environments and tools, and packaging services as well, so that researchers can take their concepts through to prototype and demonstrate them in an application context or system context to reduce the risk and project timelines. We source supply from across around the world in terms of CAD tools, fabrication services, packaging, test equipment and test services. We also work with 35 university labs across Canada doing micro or nano fabrication. And Interposer technology is becoming available as one of the platform technologies that we provide to Canada's NDN. So as I mentioned, the Interposer platform is a platform that we've been working on for over a year to deliver a design environment for a commercially available fabrication capability that's offered by Innotime technologies. The goal of our project is to lower the barrier for researchers to design and manufacture highly integrated microsystems components and systems, supporting integration of component technologies from different functional domains such as microelectronics and silicon photonics, or integrating components from different technology nodes, such as lower cost, lower performance nodes with high cost, high performance nodes. In doing so, we want to accelerate the path to commercialization by leveraging commercially accessible and scalable sources of supply in terms of CAD tools, PDKs and manufacturing capabilities, and provide a means to realize the system prototypes for pre-commercial field trial demonstrations. And we also want to leverage manufacturing capabilities in Canada, including M&T labs, such as 3IT in Sherbrooke, which is one of the suppliers in this manufacturing chain. We want to provide this as a modular flow where other M&T labs can participate in unique or complementary services to expand the supply network for this Interposer platform. And specifically, this project aimed to deliver a design front end in terms of CAD tools and a PDK for the Interposer manufacturing product and service offered by Innotime Technologies. And this is leveraging CFI funds through the MSys Canada or Embedded Systems Canada CFI project and future enhancements through the CFI Adapt project, which CMC is managing. So I guess I'll turn it over now to Frederick Kalinian from Innotime Technologies to go over the technology overview of the platform.
Thanks, Hugh. Okay, so my screen's up and running. Hugh, you see it well?
Yes, it looks good.
Okay, thanks. All right, hello everyone. I'd like to thank you for attending this session. I'm Frederick Kalinian from Innotime Tech, and we're presenting our work and fabrication offering for the rapid physical prototyping platform for incompatible microelectronics devices. It's a long title for actually an obvious platform. It's a 2.5D multi-technology silicon interposer platform. This is made possible with our partners CMC and of course our collaborators SoftMem, Spark Micro, and several of the researchers at 3IT, as well as the early adopters of the toolkit, which make all the feedback that we're experiencing possible. A short outline, just we're going to present who we are quickly, what we're doing as usual, why use the interposers, how we do it, and some of the platform specs, some of the new specs that we've put out there from the early feedback we got from the PCM and the early adopters, and the current status items. We'll go through a checklist of what things are looking like right now. So Innotime Tech is a technology integrator. We work with a network of partners to deliver microelectronics projects, MEMS, nanomaterials. We currently focus on high throughput, low power industrial sensors, try to bring those two worlds together. Some embedded AI sensor nodes, custom MEMS devices, and of course, our large focus is on the 2.5D silicon carrier platform that we're going to talk about today. So specifically what we do, we help teams refine their specs, get a first prototype going, characterize the product enough to get a cost-efficient path to commercialization, and when the time comes, help them gain access to high-volume suppliers. So our approach is quite simple. What we do is we create a tile with a rectangular array of TSVs, a little bit similar to a breadboard. And what we do is we offer standard tiles on a 19 by 19 array to get a density of about 360 TSVs per square centimeter. And we also do custom size tiles, as you'll see ahead. So we start off with a 6-inch wafer. We uniformly cover the wafer with TSVs. So we don't put in any scribe lines. So we remove all the limitations when it comes to custom dimensioning. So what we're able to do is offer both standard tiles and custom sized tiles according to your needs. As you'll see here, these are some of the cutouts of the standard tiles. We have a single tile 1x2 or 2x2. Now we have a varying amount of TSVs according to each cut. Now this approach means that we can inventory your tiles. Now that seems benign, but what's the benefit to you? Well, actually, we reduce the cycling time and you get your prototyping out in about 5 weeks. So that's a very quick turnaround time, which is our focus, developing this process. And with when it comes to testing with standard tiles, we can get you standard test sockets, which are available. But with custom tiles, well, custom test sockets will be required, and we'll be glad to supply those to you as well, so you can test your system, your multi technology system. Now, when it comes to custom sizes, you get to choose your dimensions, and we offer full or quarter wafers as well. You can get the benefit of extra flexibility and avoid unnecessary overbooking on the wafer this way. For a cross-sectional view, okay, so we offer, the Interposer platform naturally offers very small sizes. This represents about a 10 times reduction when compared to a PCB signal routing, and about a third of the thickness of a typical bare die. When you look at the cross section here, on the top side we have 2 RDLs. On the bottom side we have another redistribution layer, which is called BMET1. The TSV diameters are at their circular TSVs at 100 microns with a pitch of exactly 500 microns. And we can go down to about 5 microns of metal width. So that's, as I said, 1/10 of what you can do on a PCB technology. So as you mentioned, the production process is broken into modules. So this way we can allow for flexible manufacturing. The first module is, of course, the TSV array formation. Top side patterning comes after that, then the bottom side, and finally component placement and assembly. With our modular manufacturing approach, the designs can be fully completed with us at Innotime and 3IT, or they can be handed off to qualified labs across Canada, including yours, if you're a lab or a fab manager, of course. We can get your wafers partially patterned, so we can interrupt the fabrication process at any point, and then you can take over with your requirements and your lab. So we can hand off individual tiles. We prefer, of course, quarter wafers or complete wafers. It's much more easy to handle, and your visiting equipments can easily handle. Most probably quarter wafers would be the best way to go. So the fourth process step, which was the component placement and assembly, our preferred option is flip chipping, because it takes totally advantage of the space savings that you get on a silicon platform. If you want to do wire bonding, of course we can, it's up to you to decide how you want to do that. We can place standard 350 micron or 125 micron BGAs on 1,000 micron pitch with underfill, and we'll show that in the slides coming up. Okay, now we'll go through this. I guess I'll go through this quickly because I'm pretty sure all of you know why you're here. We don't need to say why you need to use the Interposer. But if you're an IP vendor, or if you're someone who has a design that you want to show, or you want to display out there, what's good is you can put your IP with all the auxiliary components around it on a silicon platform, and you can do various demos for different customers, because each customer wants their own version of a demo, right? So this will allow you to come as close as possible to your finer SoC design, let's say. And in terms of speed, size, and power, well, you're almost there. And this is the point of going on the Silicon Interposer platform. If you're, say, an SoC developer, which we've met a couple of in the last year, actually, well, again, you need perhaps to increase your speeds, to reduce power, reduce size, and perhaps you're not ready to do the jump to, say, a 28 nanometer design, and you want to de-risk things. So you can go on a Silicon Interposer platform first and perhaps do some early software development before jumping, head first into your SoC design on a single chip. So that's another advantage for SoC developers. And what's most beneficial to our audience today is also a proof of concept. So if you're a researcher, you might be looking for a low-cost way to demo your proof of concept. So using this platform, you can increase your product capabilities, again, speed, size, and power-wise. and you can demo product to a near to your sellable form, right? So you can hide all the complexities of wiring and support circuitry and make your product more attractive to buyers. Okay, so some of the advantages of using the interposers versus a PCB. Now we have we can go straight down to wiring density. So when it comes to PCBs, best efforts can give about 130 lines per centimeter square. Now with five micron lines in spacing, with a silicon carrier, we'll quadruple that wiring density to about 600 lines per layer. And this is the bottom line of what we'd like to tell you. So how we do it? We're closely aligned with our network of partners. So research and fabrication is done at 3IT in Sherbrooke, Quebec, and Microplex. We fabricate our 6-inch wafers at Microline and do silver filling of the TSVs with Microplex before they arrive at 3IT for RDL processing. As many of you have seen the Tanner design kit, the version 2016 was out at the last training session. So we enforce design rules, offer a library of standard components and common chip footprints. A cross-sectional view of some of the design rules. Also, we have DRC LVS that you can carry out before submitting your design. And we also are working on getting a migration methodology so you can migrate your PCB designs onto the Interposer platform. So you can go from PCB to Interposers in a hopefully quick step. So as we've mentioned previously, we're offering a couple of reference designs to CMC and the public. The first one is a compact BLE sensor node. It's essentially a microcontroller that gets data from an accelerometer, a light and temperature sensor. So the user can shake it, and upon shaking, the sensor node wakes up and starts transmitting data to an Android phone app. And this is actually going to be implemented onto the Interposer substrate. So we're looking forward to advancing on that. We have more details coming up in later slides. This is the PDK, this is the design on the Interposer using TMET 1, 2, and the bottom metal layers to fabricate our BLE sensors on the silicon platform. We also have a second reference design, which is the optical receiver front end. It's basically a photodiode and a transimpedance amplifier in bare die form, which are wire bonded onto the silicon platform. And of course, the layout view and the mandatory view next to the US penny. So it's going to be quite small. So Tanner Toolkit includes free downloadable user guides, rules decks, tutorials, and the Tanner tool suite. So feel free to use them. So we're looking for more microfabrication labs across Canada to take part in our modular design flow as proposed earlier by Hugh. Each supplier is encouraged to fabricate a PCM, and depending on the nature of design, we want users to be able to select suppliers based on test chip results, skill sets, equipment. Now, some of the tests that we include in our PCM is for 4-point resistant tests, contact chains. You can do maximum current tests, CNI, or some of the S parameters you'd like to run on the with RF tests. So currently we have some test results that are out, and on the left you see we have a 4-point resistance test going on a resistive line in the center between the two metal structures over here. I think my slide here, right? So this is TMET 2. With TMET 2, we found about a sheet resistance of about 32 milliohm per square. So that's a positive result. What follows next is the same tests on TMET1, BMET1 as well, and then on towards the contact chains, how much resistance we get out of a chain of 50 TSVs, let's say, and the max current capabilities of our lines as well. Now we did during our PCM run, our first PCM run, we had to do a small adjustments in our design rules. So what we had are, if you see on the left, we have the top TMET1 to TMET2 contacts. So these are contact arrays that were defined at, I believe, at about 5 microns per side. So that array couldn't etch properly. So the top side, we have a proper etch. The bottom side, there was some difficulty in etching. So we did change design rules in order to have a larger dimension in that contact, in those contacts. So we're aiming more for a single large contact instead of a smaller array. So that was a positive change we did to our PDK to avoid this design error to spread over to everybody's designs. Now, the second design change we did is we're going to try to avoid putting contacts directly over TSVs and avoid passing a second metal layer directly over TSVs as well, just in case there's variations in the silver fillings in the TSVs. This won't affect our metal layers, TMET2 and TMET1 going above it. All right, and another design rule we put in, we'd like to limit the design area to 9.5 millimeters per side on a 10 by 10 tile. So users who are just at the limits, we encourage them to shrink their designs to 0.5 millimeter off the edges to avoid any issues during the RDL. All right, so some of the platform specs, we've updated some of the features, so I'll get slightly more into it. Many of you were there during our training session, I believe, and you saw some of the rules. And if you remember them, great. If not, well, this might be new to you. I have a cross-sectional view of our top flip chip pads that we propose. These are standard sizes that we have. You can instantiate them in the PDK. So we have 75 to 125 micron per side for a flip chip pad on a 150 micron pitch. And this is etched in the top passivation layer where the TMET2 is exposed. Now the material of the pad is, we're using aluminum, and you have the option, if you like, to add gold if it's in your preference. Now recall that this is it's a standard cell, so you can just instantiate these, pardon me, and do your design fairly quickly. However, you can bring these sizes much lower according to the specifications in the rules deck. So we can talk about that later if you have any questions. Another view is the bottom side view. And I believe many of you have asked questions about this previously. So what we're offering are fixed sizes for BGA, and these can't be modified. So you have two options. One option, 350 micron ball, which will sit, I'll get my pointer, which will sit on a 300 micron per side pad, or a 100 micron pad for a 125 micron BGA. All right, so this in blue is the bottom passivation layer in which we etch, and then we etch that to reveal the BMET1. And for both of these structures, you see we have a 1,000 micron pitch. And this is fixed, unfortunately, for the moment, for the sake of consistency and getting working prototypes for all our customers. We'd like to keep the bottom side fixed. And of course, in the future, we tend to go smaller, but for now, we're starting with this. Moving on to the next slide. So another small, an important change we did is the TSVs. So we're using 100 micron diameter TSVs filled with silver. This is with the help of Microline and Microplex. And they're at their distance at a 500 micron pitch. And there's no There's no polymer fill. It's completely filled with silver, if you had a question about that. Moving on. All right, so our current status, well, to look over some of the items I'm going to talk about, it's the PCM2 fabrication and the PDK release, which is up. New specs sheet are out. Reference designs, we're doing some great advancement on that, and some of the users out there should take advantage of it. Early adopters designs are in progress, and we're accepting new designs hopefully in January, where we're aiming for that, and some of the online tutorials. So the new PCMs are currently in tests at 3IT, and we're looking to publish the test results in January. If we could do that at Christmas, we would, but unfortunately the labs are closed. So we're starting off last week, third week of, this week of December, and continuing in January. So we'll publish those, all the 4-point resistance results, the max current test, max breakdown voltage results. We're going to put those results out. And our main focus in the second run of the PCM is to get better contact yield, so we won't have any of the errors I showed you earlier. And of course, the low resistance across the TSVs and the RDL lines. PDK release, version 2.2 is expected to be released this week. So all the new design rules I talked about will be in there. They're not major changes, but they're important changes. And these will be incorporated in all of our reference designs. So that'll be the BLE sensor as well as the photodiode, the optical receiver. And our early adopters are currently working very hard to adjust their designs according to these specs as we speak. So they're going to run it with a new PDK, and once it's validated, the mask orders are set to be sent out third week of December or second week of January. So we're looking forward to making those designs all together. So the reference designs and the early adopters, things are looking good. And of course, if there's any questions, all early adopters are encouraged to collaborate with us, and we're on a tight collaboration schedule since it's been about 2 weeks. Spec sheet release. So the spec sheet is currently distributed, and the PDK is following up with the user's guide. And if anybody would like to have access to those spec sheets, please let us know. We'll forward you that as soon as possible. BLE reference design. So we have an early PCB version, and what we have this for is for firmware evaluation. So we're going to check how the accelerometer is working, how the data is being transmitted to the Android app, and some of the firmware files are scheduled to be released this month. And the Interposer version expected to be fabbed out February 2018. Now, CMC plans on making all the firmware available, including the design files, to any user and member of the CMC that would like to take this, modify the firmware or the design according to their needs, and drop it on an Interposer, which we'll be glad to fabricate for you. Early adopter designs, well, I'm very happy to say that Srinil from École Polytechnique and Colin Ross from Dalhousie University in Halifax are currently working on getting their designs out on the Interposer. Srinil has an on-chip infrared spectroscopy for brain imaging and optical mammography applications, whereas Colin's it's a voltage driver for deformable mirrors. Now, these are to compete with space-based telescopes, but based on the ground. So two very interesting and influential projects. We're looking forward to following on that with them through the end. Current status for the new designs. So we look forward to getting any of your new designs starting in January 2018. And all of those will need to be done with a version 2.2 of the PDK and the new user's guide. So we're asking you for about another 30 days to brush up on those, release the files and the documents, so you can do your design from A to Z without any hiccups, let's say. And last but not least, our online tutorials. We're very eager to publish these. I'm looking for February. So this way, some people don't want to go through all the users' guides all the time. and you could just look it up online and see the essentials of the toolkit, how to draw lines, how to view the layers, some of the cross-sectional views, and how to run a DRC, LVS, and the basics. And for more detailed info, of course, you can go in the user's guide. So we'll try to get about 5 to 8 videos out there, and get some feedback, of course. All right. And okay, to finish off, as usual, we'd like to greatly acknowledge our partners, CMC, Hugh, Peter, Jeet, and Bob Millard. 3IT, all the researchers working super hard to get all this, to get the platform out and to test the PCMs and work with all the masks and the layers that they know how hard they're working. So they're probably on the call. So thank you all very much. SoftMems for the PDK, online tutorials and all the advice, as well as Spark Micro for doing tests for us and making sure everything works well. Thank you very much. And at this point, if there's any questions, we're several here to answer your questions, from fab to assembly to future plans. Thanks.
Thanks, Frederick. I guess just before we go into questions, I'll just finish up with CMC's plans around the platform. So as Frederick mentioned, I guess it's version 2.2 now, but the latest version of the PDK is available now for the early adopters. And this includes reference designs, training materials, and user guide. CMC is expecting to offer a regular manufacturing service in sort of the early spring of 2018, after the reference designs and updated PCMs and early adopter designs are back from manufacturing. We would also expect to offer training and a user workshop again in early spring 2018 to complement the release of the regular manufacturing service. And as I mentioned earlier, the Adept CFI project would do further enhancements to the PDK and design environment around this platform. In terms of CMC offering services for this platform, we'd offer CAD tools and run a Interposer manufacturing process similar to what we offer for other technologies, where researchers can get subsidized access to manufacturing through an RFMR process and a peer review. We offer the CAD tools, the PDKs, the MPW runs for this, as well as complementary MPW runs in the technologies that researchers would use to integrate on top of the Interposer platform. Other things we're looking at is providing a component library of commercial off-the-shelf parts that would be commonly used by researchers, maybe as variants of the reference designs that are being produced. We'd also look at putting some of the processes being developed for this in the process repository that the Adept platform is also delivering, and then offering test and validation equipment and services through our equipment pool, software development kits, FPGA boards that would be able to hook up to Interposer prototypes. Innotime, as Frederick mentioned, would stock the interposers and provide and be sort of the front end for manufacturing services and commercial scale up through 3IT or as alternate processing steps at other MNT facilities across Canada. Beyond the current version of the platform, as I mentioned, we'd like to enhance the manufacturing options through additional MNT lab services. Provide test and validation infrastructure, including a fixture breakout board that can connect to FPGA or PXI test equipment. These could be accessed through the CMC equipment pool. A PCB tool-based environment, complementary to the Tanner environment as well, may be useful for some users. enhancing the embedded software development and debug environment for reference designs such as the BLE design that Frederick talked about, commercial off-the-shelf component library, and technology enhancements driven by client needs, which may include multi-chip stacking, finer pitch interconnect, alternate packaging solutions, and all additional technology domains that can be integrated on the Interposer. I mentioned the Adapt CFI project is the main source for further enhancements to this platform. For more information, in the CMC hub, or the NDN hub, there's a group for the Interposer platform where we would post the specifications for the reference designs and as well as the platform, and we'll be updating this with the new specifications soon. If you have any more information on, or any more questions on the platform, you can contact Jeet Narsingani from CMC Microsystems or myself. We can put you in touch with Innotime or answer questions. So that's it from me. If folks have any questions in the chat.
So I don't have.
I don't see any questions coming up.
Yeah, no, I don't have any question on my side. People can unmute them if they want to ask questions.
If anyone has any questions, they can unmute themselves as well if they want to ask. Yes, otherwise, we'll
Cheat as a question.
So the question is flip chip an option in the near future?
Well, flip chip is is what we're offering. It's not necessarily in the future. We can start off with flip chipping.
Okay.
And the option is open to anyone who wants to use it. Of course, the 3IT has the capability to do flip chipping. And as long as it's within the specs that we publish, then there shouldn't be any trouble going forward.
Okay.
So I have a question from Srinil, I guess. It's a private question, but I think it's worth mentioning. We couldn't do an LVS at the time of the last tutorial. Can we do that now? So the LVS capability is there. However, there's no one button method to do it at the moment, but we're working hard to get it to interface with the Tanner platform rather in a more easy way. But I'll definitely share that info with you offline, Srino, of course. But for the tutorial, for the training session, I mean, it was not something we can show in a very quick manner. We were pressed for time, but we'll be glad to share that info with you. I believe also, oh, yeah, that's a question I have.
So would the LVS be covered in any of the training videos that provide?
Yes, so the LVS in the videos it would be in the videos. We're aiming for that to facilitate, to make it more easier for the user to apply that, to do that check. Yes.
Okay.
There's some new members have had questions. I think it's to go up.
Okay, well, if no one else has any questions, I guess we can sign off. I'd just like to say thanks for your time, and if you have any questions or want to get access to the PDK or any of the capabilities, please contact myself or G in the time. Okay. Thanks a lot.
Thank you very much.
Thanks, Frederick.